Good afternoon. I'm Mingyu Choi, the second author of this paper. Today, I'd like to introduce PeRF, Preemption-enabled RDMA Framework. RDMA provides high throughput and ultra-low latency through zero-copy operations. This performance leap is made possible by the kernel bypass mechanism, allowing direct data transfers between host memory space and RNIC without involving OS kernel. This efficiency makes RDMA ideal for data-intensive applications like big data analysis, machine learning, and distributed storage. However, the kernel bypass feature is a double-edged sword. While it offers significant performance benefits, it becomes challenging to properly manage the RDMA flow since RDMA works outside the OS's control. Consequently, it introduces challenges in security, scalability, and especially in performance isolation. To understand the behavior of RNICs, we conducted micro-benchmark tests to uncover the scheduling mechanism employed by RNICs. Our setup included a 16-core Intel i7 processor, 32 GB RAM, and a Connect 6 100 Gbps Rocky NICs. In our first experiment, two applications share an RNIC. One sends small messages of 16 bytes each, while the other sends large messages as background traffic ranging from 64 bytes to 1 GB. We used MTU sizes of 1, 2, and 4 kilobytes, respectively. The graph shows changes in the message rate and average latency of the small message applications depending on the background traffic size. We observed that the larger the size of the background traffic, the worse the performance of the small message application. Interestingly, the performance begins to remain stable once the background traffic reaches MTU size. From these observations, we suggest that RNICs evenly process MTU segmented packets from various queue pairs. In the second experiment, we ran 5 applications sending messages of 16 to 256 bytes in batches. And then we introduced additional message flows of 1, 2, and 4 kilobytes, respectively. Without the presence of a large message flow, all 5 applications achieved their maximum message rate. Surprisingly, when they are running with a large message app, the message rate of all 6 applications decreases to match the rate of the large message app. We analyzed the reason for this overall decrease is that QPs might be stalled while the RNIC processes the larger message app. From these observations, we concluded that the RNIC uses a round-robin scheduling method when managing multiple QPs. Based on this RNIC scheduling behavior, we categorized applications into more detailed groups using message level and QP level criteria. At the message level, we identified 3 types of applications: bandwidth intensive or BAP, message intensive or MAP, and lastly, delay sensitive or DAP, depending on their message sizes and sparsity. At the QP level, we distinguished between applications using a single QP and those using multiple QPs, resulting in 6 types of applications. In this paper, BAP sends 1 megabyte messages by default, while both MAP and DAP send 16-byte messages. And only MAPs transmit messages in batches of 32. With these application types, we conducted various tests and identified some anomalies. At the message level, bandwidth-intensive applications degrade the performance of other apps when sharing the RNIC. In our test, BAP was barely affected, while MAP's message throughput decreased by 3.8 times, and DAP's average latency increased by 6.1 times. At the QP level, apps using multiple QPs monopolized RNIC resources, affecting the performance of apps using a single QP. This trend was consistent across different types of applications. As a result, RNICs do not provide performance isolation when multiple applications share RNIC resources, failing to support multi-tenancy. Many studies have been conducted to overcome the limitations of RNICs. These were mostly done in two ways, by directly modifying hardware or by developing user-level software due to the kernel bypass nature of RDMA. Hardware-based solutions offer strict performance isolation, ensuring each tenant receives guaranteed resources. However, they struggle to adapt to dynamic network requirements. Conversely, software-based solutions adapt well to network changes, but rely on reservation-based resource allocation. This requires continuous estimation of available resources, leading to inevitable performance degradation. Under non-work conserving method, resources can stay idle, even if there are pending tasks. This aims to ensure fair resource sharing and performance isolation, but can lead to underutilized capacity. Therefore, we propose PeRF, a preemption-enabled RDMA framework that retains the flexible advantages of software-based solutions, achieves bare metal performance by preventing RNIC resources from being idle, eliminates the need for network resource estimation, and remains completely transparent to applications. Before delving into the core details, it's essential to understand the concept of preemption. In computer science, preemption refers to the ability of an operating system to temporarily interrupt a currently running task to run another task. In our early findings, we observed that the anomalies in RNIC stemmed from resource contention between tenants sharing the RNIC. Our research began with the idea of introducing preemption to address this resource contention in RNICs. In this study, preemption in RDMA refers to interrupting a message and prioritizing another in RNIC by leveraging a managed QP and a combination of specialized work requests. To implement preemption in RDMA, we use managed queue pair and specialized work requests. Here's how an application processes work requests with an RNIC. The application registers a work request in the host memory and triggers a doorbell on the RNIC. Then, the RNIC detects the new work request and fetches it from the host memory. Typically, this happens in one go without interruptions. However, in managed QPs, the doorbell must be explicitly triggered by using an enable work request. Let's take a look at an example of enable work request. When an application creates a QP in managed mode, any work request posted to the QP by the application is stored in host memory instead of being directly sent to the RNIC. For the RNIC to fetch these work requests, an enable work request must be issued separately in master QP. Before explaining the wait work request, let's look at what happens after the RNIC processes a work request. Once the RNIC processes a work request, it generates a completion queue element, or CQE, in the specified completion queue. The application then polls this CQ to check the number of CQEs and verify if the work request has been processed. A wait work request pauses the processing of current QP until the specified number of CQEs in the target CQ is reached. For example, the RNIC will process work requests until it encounters a wait work request. When it reaches the wait work request, the RNIC will pause processing work request from that QP and wait for the CQE in the target CQ to be polled. Once the specified number of completion queue elements has been polled, it will resume processing the next work request. Based on these specialized work requests, PeRF implements preemption at both the message level and the QP level. First, at the message level, when a bandwidth-intensive application sends a message, we break the message into equally sized sub-work requests. Then we interleave these sub-work requests with zero-wait work requests. A zero-wait work request is an operation that completes immediately when posted to the QP. This temporarily pauses the QP and gives other QPs the opportunity to be processed first. Using this method, we ensure that applications sending smaller messages like DApp and MApp get more chances to transmit their messages. At the QP level, we design a pause-resume operation to implement preemption between QPs. For example, let's consider an application using 4 QPs. PeRF creates an additional managed QP called the preemption control QP along with the preemption control CQ. We prefill the host memory with 0 work requests, which are 0-byte messages looped back, containing only a header without a payload. Now, suppose all QPs are filled with following work requests, and the RNIC is taking turns processing each of them. When the RNIC encounters a wait work request, it immediately pauses that QP. Currently, all QPs except the first QP are paused due to the wait work requests. When the RNIC encounters an enable work request from the first QP, it fetches the 0 work request from host memory. These requests are immediately completed, generating CQEs. As the CQEs accumulate, the wait work request in the second QP is completed. Then it resumes processing subsequent work requests. Now let's take a look at how PeRF schedules at the message level. PeRF's large message scheduling engine isolates DApp and MApp from the large messages of bandwidth-intensive applications. It achieves this by breaking down large messages into smaller sub-work requests. And these smaller requests are interleaved with 0-wait work requests. As a result, while the work requests of BApp are temporarily paused, other smaller messages get more opportunities to utilize the RNIC through preemption. When an RNIC is shared between a multi-QP app and a single QP app, PeRF initiates the QP-level isolation process with multi-QP scheduling engine. It can control the number of active QPs by using a combination of pause and resume operations. The picture shows a multi-QP app using 4 QPs. The multi-QP app takes turns activating QPs by toggling pause and resume. With the multi-QP scheduling engine, PeRF can limit the number of active QPs for a multi-QP application, effectively implementing QP-level preemption. This is basic architecture of PeRF. We divide PeRF into onloading and offloading processes to minimize the overhead of data plane. The onloading process runs on the main thread and handles lightweight tasks like intercepting application verb calls, estimating message sizes, and counting created queue pairs. Additionally, it enforces network policies set by the administrator and dynamically triggers the isolation process based on the application type. The offloading process manages more complex tasks on background threads. It involves a PeRF master thread that manages the global state of tenants and coordinates worker threads. With just a single dedicated CPU core, the offloading process operates well even when managing more than 1,000 applications simultaneously. In the evaluation, we conducted experiments using the same setup described in the background section. We compared PeRF against hardware isolation schemes to establish a baseline. The strict policy, or SP, schedules messages using priority queues. In this test, we configured SP to strictly prioritize small messages. On the other hand, enhanced transmission selection, or ETS, uses a weighted round-robin queue for scheduling. We assigned a bandwidth weight of 16:1 to BApp and MApp, which showed the optimal performance for both applications. First, we measured the performance of default RDMA, SP, and PeRF when BApp and DApp are competing. In this scenario, PeRF, a software-based solution, achieved throughput and latency comparable to SP. Next, we compare the performance of default RDMA, SP, ETS, and PeRF when BEP and MEP coexist. SP, that prioritizes small messages, allowed MEP to dominate the RNIC. It significantly reduced BEP's throughput. Conversely, ETS achieved high throughput and message rate by adjusting the weighted priorities of BEP and MEP. PeRF showed performance close to that of ETS in this scenario as well. Hardware-based schemes usually perform well in particular scenarios and settings. However, PeRF is a flexible software-based solution that provides hardware-like performance in a variety of scenarios. We evaluated PeRF's effectiveness in providing message-level isolation using a comparison with Justicia. Justicia is a token-based software framework that ensures fair RDMA resource allocation among tenants. It calculates and adjusts work request rates to mitigate network congestion and maintain fairness. Justicia R is a relaxed version of Justicia, which is introduced in its paper. It allows more throughput for bandwidth-intensive applications with a higher latency threshold. First, we tested with BEP and MEP sharing RNIC resources. Justicia reduced the work request posting rate of both apps to around 50%. In the same condition, PeRF achieved significantly higher throughput and message rate. Next, we evaluated the scenario with BEP and DEP coexisting. Original Justicia reduced BEP's throughput again to maintain low latency for DEP. Although Justicia R achieved higher BEP throughput due to its generous latency threshold, it performed worse than PeRF in both throughput and latency. This is because, unlike Justicia, PeRF uses a preemption mechanism that allows continuous work request postings, enabling efficient work-conserving scheduling. PeRF's advantages in isolating multiple QPs are also clear. In default RDMA, as the number of QPs used by BEP increases, MEP's performance gets worse. In case of Justicia, it allocated RNIC resources fairly by reducing the performance of both applications by half. However, by employing work-conserving preemption, PeRF increased both throughput and message rate, and it achieved higher resource utilization. This trend was similar for MEP using multiple QPs as well. We also examined the behavior of real-world applications when various schemes were applied. For this experiment, we selected 3 applications: Apache Acryl as BEP, HERD as MEP, and RPing as DEP. As shown in the topology, we ran these 3 applications simultaneously, sharing RNIC resources of the client node. The results showed that PeRF achieved relatively better performance across all applications. Original Justicia had a slightly better average latency for RPing compared to PeRF, but Acryl's throughput was significantly lower. Conversely, Justicia R's Acryl showed similar throughput to PeRF, but PeRF had better latency for RPing. And PeRF achieved the best message rate for HERD in all the cases. We've conducted various other experiments to validate PeRF's functionality. For detailed results and analysis, please refer to our paper. In conclusion, traditional RDMA solutions often experience performance anomalies and inefficient resource use in multi-tenant environments. PeRF effectively addresses these problems with its innovative RNIC preemption mechanism and work-conserving packet QP scheduling. This ensures software-based performance isolation without compromising RDMA's high performance. You can try PeRF at the following GitHub link below, and this is the end of my presentation. Thank you.